Okay, so here I intend to give you an introduction to quantum mechanics. And this is pretty quantitative, but I guess I'll add some qualitative account of what's going on here. The book that I'll be referencing throughout this entire playlist is Modern Physics by Jeremy Bernstein. It's a great book, gives you a huge insight into what modern physics is, where it comes from, how it developed, because he gives you a very historical account of the way things developed, as is appropriate, so that you can understand. Anyhow, I'm just going to start right in on chapter 4, which is called Waves as Particles and Particles as Waves. So I'm just going to say duality of everything. And this is a name that I made up, kind of, but it seems really appropriate to me because the entire motivation behind quantum physics is, you may have heard of the wave-particle duality of light. Wave-particle duality of light, and this is an idea that has been known since the early 1900s, even before quantum mechanics was developed in full. But the idea behind quantum mechanics is that there's also a wave-particle duality of particles. And so basically, everything that you know about light, so you can treat it as a wave, you can treat it as a particle. It it can behave in both manners. Similarly for particles, for everything that exists in the universe, everything is supposedly composed of a particle, but these particles also have wave-like properties, which is super weird. But basically everything that you did in electromagnetics or any course where you'd have learned about the behavior of light, you can extend that same line of thinking to the realm of particles. And so it's kind of a crazy abstract notion, but I'll try my best to develop this mindset for you, why this was even conceived of in the first place. As a matter of fact, since there's so much convincing evidence out there for whether light is a particle or a wave, I'm just going to touch on a few things, and you can look it up and hopefully find something interesting that convinces you. One of the interesting experiments for light being a wave is the Fresnel spot, which is if you have this disk, right, and light is a wave, it's coming down this direction, hitting this disk. Classically, what would happen is, if the light's coming straight down on it, and this is the ground, you would only see light right around here, right around here, and obviously where the disk is blocking it, there would be no light. But interestingly enough, since light is a wave and not a sum of particles that are just going down and bapping off the top of this thing, being reflected, and only the ones that are at the edges of the disk are coming down here. Maybe there's some kind of light coming from this direction down this way. But since light is actually a wave, what happens is there's an interference pattern that produces this hugely bright spot on the ground. It directly underneath the center of the disk, where it should be its darkest. What you see is a really bright spot. And you can actually do this experiment yourself with a laser beam and a disk. It has to be a laser beam or something that has a single frequency, because if you just do it with like a light bulb, the different frequencies screw up the experiment and you end up not seeing anything. But that aside, the Fresnel spot is, there are videos of it on YouTube and everything, so you can probably just look it up like right now if you want to. And it's pretty interesting to think about. But of course, there's other evidence for whether light is a wave or not. One of the ideas for whether light is a particle is just the idea that there used to be this ether theory that dictated that light's a wave. waves propagate through a medium. That's the false assumption, is that waves propagate through a medium, but that was the assumption, and therefore that medium is the ether. And it turns out that the ether theory was entirely wrong, that light doesn't need a medium to propagate through. But it having been found out that light doesn't need a medium to propagate through, well, what people said was, well, then light has to be a set of particles, because particles don't need a medium to propagate through, which is a correct assumption. But that was just one of the lines of thought behind whether light was a particle or not, or a wave or not. The most important thing to get to is the Young's double slit experiment. And so all I'm going to say about this, I'm going to dive into this pretty deeply, actually. There's some math behind it and things about the interference patterns, because you'll probably get into this in an electromagnetics class, or your light optics courses, or anything dealing with introductory wave notions. The Young's double slit experiment is this: if you have a source of light, right, and it's emitting light like so, and it comes upon a wall that has two slits in it, and so we're going to call these slits, the opening in the slit this is a distance, let's call it h, actually. This is a width h, and this is also width h. They're the same. It's assumed that this wave is uniform, so the light entering this hole is the same as the light entering this one. And we're gonna have a slit separation A, and those are going to travel. The light is going to come out. It's going to kind of spread out like this, and we have this distance. So we can just call this L. We don't really need this distance so much as this one, which is the light from this hole to a spot on the wall, and the light from this hole to a spot on the wall. So this is a point P on the wall, and we'll call this X. So if you go along X, so this is X equals, this will be X equals 0, and then this is X increasing, so positive X, and this is negative X. That should probably be consistent. Positive X and negative X. So this would be like X equals -1, for instance, -2, +1, +2, or whatever the case may be. The Young's double slit experiment, though, what it is you have waves coming out of both of these slits that are being diffracted, and what you ultimately end up seeing is peaks and troughs of the light intensity. So you see, I'm going to make what's called an interference pattern. So it's really bright in the middle, dark right here, bright right here, dark right here, bright, dark, bright, and the same way, dark, bright, dark, bright, dark, like that, and it just keeps going along the wall this way. So what the Young's double slit experiment shows is that light behaves as a wave. It comes through these two slits. The waves interfere with each other, and there are points where it's super bright because the waves are constructively interfering, and super dark because the waves are destructively interfering. And there are a few important equations to keep in mind while doing calculations for the Young's double slit experiment, and we will get into those in the next video.